Next topic we look at are parametric equations and plane curves. Parametric equations and plane curves. So if we have a graph, x and y, and let's suppose that this represents some type of projectile motion or the path of something. You can think of it as starting, going up a hill, reaching the peak of a hill, and coming down, um, driving along a road or something. Um, this equation, we think back to 10.1, would give us the equation for this graph. If we consider the vertex to be at 4, 4, if we put a 0 in for y, 0 in for x, we get 16 on this side, 16 on that side. So that does go through the origin. So this equation in this form, or if we solve that for y, think of it in the form we thought of equations in back in 112 pre-cal. Either way, while those equations might describe the path of an object, it doesn't really give us the whole picture. It doesn't tell us how quickly our object follows this path. We don't know if it goes really slow along the path or if it's going really fast along the path. So in order to describe that, we need to know, well, how are those two variables related to t? How is x related to t and how is y related to t? And what we can do is we can have equations in terms, an equation that tells us the horizontal position in terms of a variable t and the vertical position in terms of t. Now, that could correspond to two different graphs if you wanted to. We could graph, back in Cal 1, we talked about position versus time graphs. And that just described one-dimensional motion. It described how far we were along a path over a particular time, but we could do that for the y direction and the x direction. Or we can put those together, x and y, so that we get a better picture of what the motion actually looks like. These graphs just help us to see what the rate of change in the x direction and the y direction are. But here, it lets us see what the actual path of the object is. But we still often are concerned of, well, how fast are we moving at any one point? So let's look at an example. If we have x of t described by t, y of t described by 2t minus 1, and let's let t go from 0 to 3. So let's make a table. Let's make an XY table, and let's put a third column in it that represents different times. So our time is going to go from 0 to 3 seconds. So when time is 0, 1 second, 2 seconds, 3 seconds, we could also look at smaller unit or smaller partitions. But let's just pick some random t's in this interval and find out for each of those t's what's the corresponding x and y. So if we put a 0 in to this function, we get 0. If we put a 0 into this function, we get minus 1. If we put a 1 into this function, we get a 1. A 1 into this function, we get 2 minus 1. If we put a 2 in, we get 2, 3. If we put a 3 in, we get 3. And then into that one, we get 5. So if we plot this on an XY plane, these are our ordered pairs. These are the corresponding times for each of those ordered pairs. So let's pull up a graph. Let's copy this over. So we start out at 0, -1. That's our starting point. Then we go to 1, 1, to 2, 3, and to 3, 5. So we travel along that path. And notice we did this point first, then that point, then that point, then that point. If we're concerned about the motion and the direction of the object, it started here and it went in this direction. So we could figure out how far it went. We could also figure out in which direction it went. It went from here to here, not here to here. So that would be the path described by that parametric equation over the time interval from 0 to 3. Now, the set of equations, those are called parametric equations because there's some parameter that we substitute in, and that's what links these two equations. The combination of the parametric equations and the graph that's a result, that's called a plane curve. Now, sometimes we might have a reason to want to remove the parameter. If we don't want to have to plot just tons and tons of points, we might look at those equations and say, well, I just want an idea of what the path looks like. I don't have to have all the details, but I do want to know in general what the path looks like. We can remove the parameter. So our first equation is x equals t. The second equation is y equals 2t minus 1. So when we remove the parameter, we want to pick one of the equations to solve for t. Notice this equation is already solved for t. And then we substitute the corresponding value in for t in the other equation. So t is the same thing as x, so where we have a t, we put an x in. So that's a parameterless, or that is the corresponding equation once we have removed the parameter. Notice that's just a linear equation, a y-intercept of -1, a slope of 2, which is what our graph looks like. It has a y-intercept of -1, a slope of 2. But our graph is very specific to the parameters. It goes through the duration from t equals 0 to t equals 3. It doesn't go on forever in both directions like a regular line would. It has a stopping point and an ending point, and that's connected to the parameter. So let's look at another one. Let's do let me think. X of t equals, let's do t squared minus 1, and let's let y of t equal, let's do 2t. And let's let t go from -1 to 3. So if we make a table, let's do t, x, and y. So let's do -1, 0, 1, 2, and 3. If we substitute a -1 in, we get -1 squared minus 1 is 0. let's just go down through and do all the t's here. If we put a 0 in, we get -1. Put a 1 in, we get 0, 3, and 8. Then if we take these t's and plug in over here, we get -2, 0, 1, 4, 6. So those are some points of our plane curve that correspond to t being between -1 and 3, x being described by this curve, y by that one. So let's plot those. So we're going to start at 0, -2. That's our starting point. And then we're going to go to -1, 0, then 0, 1, 3, 4, and 8, 6. So we get, did I do one of those wrong? I can't count sometimes. Let's see. If we put a 0 in, or a -1 in, we get 1 minus 1. We put a 0 in, we get -1. We put a 1 in, we get 0. Oh, here's the mistake. This is supposed to be a 2. So 0, 2. So we went, here was our last one. So we started here, and then we followed this path. And that's where we ended. So we had an initial and a final part of our curve. Now you might notice that that looks kind of like a sideways parabola. And if we come over here and remove our parameter, that's exactly what it is. If we take y equal to t and solve for t, t is y over 2. And then if we substitute that in for t here, t, so y over 2 squared minus 1. So x is y squared over 4, or we could call that 1/4 y squared minus 1. So this x equal y squared, remember if it's the y that's being squared instead of the x, that's a sideways parabola. Let's see. Notice our vertex is to the left 1, up and down none. Nothing is added or subtracted from the y, so no vertical shift. We have a horizontal shift to the left 1. But that's our the portion of that parabola that corresponds to our time frame, -1, 3. And time frame is important. If you think about dropping something off the top of a building, let's say it started here, and then it began to fall, it's going to stop, hopefully, when it hits the ground, not keep on going. Now, if we came up with an equation to describe that curve, just a regular equation, it would make up for the whole parabola. It would go on this side, it would also continue to go this way. But if we were able to get that as a parametric equation, an x in terms of t, a y in terms of t, then we would only cover a very specific time frame from its starting point. Let's say that's when time was 0, to whenever it hit the ground. Let's just call that time B. So even though technically the curve might be, the domain might be negative infinity to infinity, the relevant domain is from here to here over a specific time frame. Let's look at another set of parametric equations. Let's look at x equals sine theta. Let's do 5 sine theta. Y equals 3 cosine theta. And let's let theta be between 0 degrees, 360 degrees. So keep in mind that when we plot this as a parametric, we're going to plot an x and y. Now, we have a parameter theta that we're going to vary, but when we plot values, we're plotting x and y values. So, in trig, if we graphed that equation, y equals 3 cosine theta, that would correspond to some curve that looked something like this. If we plotted that in trig, then that would give us some curve like this. But what we're wanting to do is not plot theta as an angle. We're just wanting to let that be the parameter that relates x and y. So let's make a table. And probably the quadrantal angles will be enough here. If we do 0 degrees, 90, 180, 270, and then back to 360, then sine of 0 is 0 times 5, so still 0. Cosine of 0 is 1 times 3 is 3. Sine of 90 degrees is 1 times 5. Cosine at 90 is 0. Sine at 180 is 0. Cosine at 180 is negative 1, so 3 times negative 1. At 270, sine is negative 1. Negative 1 times 5 is negative 5. Cosine at 270 is 0. Back to 360, sine is 0. Cosine is 1. So we get points. So we want to plot this. So we begin at 0, 3. And then we go to 5, 0. Then to 0, negative 3. Then to negative 5, 0. And then back to 0, 3. So if we trace that along, let's draw that first. That's going to be an ellipse. And it started here, and it appeared that that went clockwise. Like so. So that's for theta, not t. Theta being from 0 degrees to 360 degrees. Now, if we only wanted 0 degrees to 180 degrees, then that would just be the first part of it there. Just depends on which section we want. Now, let's look at removing the parameter. Different ways we could do that. One thing that we know is that sine squared plus cosine squared is always equal to 1. That's the Pythagorean identity. So if we solve this for sine, sine is x over 5, so if we take that and square it, if we solve this for cosine, cosine is y over 3, square that, that equals 1. So we get x squared over 25 plus y squared over 9 equals 1. Notice this is the equation of an ellipse centered at 0, 0. The major axis is in the x direction and it goes left and right 5 units. The minor axis is in the y, up and down 3. Left and right 5, up and down 3. So that's our ellipse. So lots of different shapes that you can get using parametric equations.